So it's my pleasure to welcome Jesse Madnick of the University of Oregon, speaking on the Morse index of quartic minimal hypersurfaces.
Yeah, so I'd like to thank the organizers for the opportunity to speak here. I think this is my second time speaking at the virtual seminar on geometry with symmetries. The last time was a few years ago when I was based in Asia. So thank you very much for having me back. It's a pleasure. Yeah, so I'm going to talk about the Morse index of quartic minimal hypersurfaces. And everything I'm going to say is joint work with Gavin Ball and Uwe Semmelmann. So before we get started, I just want to make sure we're on the same page. I just have two slides to set notation and just review some foundations. So this is a talk that's motivated by the extrinsic geometry of hypersurfaces. So let's just review a couple of elements about that. Let's let M be an oriented Riemannian manifold of dimension n, and let's let nabla be its Levi-Civita connection. In this talk, we're going to consider compact oriented hypersurfaces and denote them as sigma. By a hypersurface, I just mean a smooth submanifold of codimension 1. And we'll let nu be its unit normal. So the extrinsic geometry of sigma, the hypersurface, is completely encoded by this tensor called the second fundamental form. The second fundamental form eats two vectors and spits out the covariant derivative of one with respect to the other, dot product with the unit normal. And this is a symmetric bilinear form. Okay, it's not obvious from the definition that this is symmetric, but this is basic fact that we learn in the first course on Riemannian geometry that this is in fact a symmetric bilinear form. And when you have a symmetric bilinear form, you can study it by looking at its eigenvalues. The spectral theorem tells you that you have real eigenvalues. Those carry a lot of geometric information. We'll call those the principal curvatures. Okay, so the principal curvatures, kappa 1 through kappa n minus 1, right? Those are the eigenvalues of the second fundamental form. Notice that the principal curvatures need not be distinct, right? The eigenvalues don't have to be distinct, and we'll come back to this point later. Okay, we can summarize the data of the second fundamental form even further. We can come up with other summary numbers. So for example, we can take the trace. The trace of the second fundamental form is called the mean curvature. And of course, it's the sum of the eigenvalues of the second fundamental form. So it's the sum of the principal curvatures. Okay, so this talk will concern minimal hypersurfaces. Okay, so what's a minimal hypersurface? So let's say we have a hypersurface, we let iota denote the inclusion. A variation of sigma is a one-parameter family of submanifolds, iota sub t, where iota sub 0 is iota. Okay, we'll let sigma t denote the image. Then we'll say that our given submanifold sigma is minimal if it's a critical point of the n-1 dimensional area functional. So in other words, the derivative at time 0 of the area of sigma t is 0 for all variations. Okay, so this is a condition. This is a variational condition. And you might wonder, how do you actually work with this variational condition? Well, requiring that working with a critical point of a functional is equivalent to working with the Euler-Lagrange equations of that functional. And in this case, the Euler-Lagrange equations are exactly the condition that the mean curvature vanishes. So that's a second order PDE. Okay, so being minimal is equivalent to the mean curvature vanishing. But in a sense, the word minimal is maybe not the best choice of words, right? As we teach our calculus students, the first derivative being 0 does not imply that you're a minimum, right? That gives you a necessary condition, but not sufficient. And so, of course, other necessary conditions come to mind to have a minimum. So for example, if you have a minimum, then for sure the second derivative is non-negative. So we'll say that a hypersurface is stable if its first derivative of area is 0 for all variations at time t, and moreover, the second derivative of area is non-negative for all variations. Okay, so this is just background. This talk will be in 4 parts. In the first part, I want to discuss just some general features of minimal hypersurfaces and round spheres. Then I want to specialize to the case of interest, which is that of isoparametric hypersurfaces and spheres. Okay, so I'm not going to assume any familiarity with isoparametric hypersurfaces. In fact, the speaker myself I'm not an expert on isoparametric hypersurfaces. I frankly just learned about these maybe about a year or so ago when starting this project, and was amazed to discover just what spectacular geometric objects they are. I wish I learned about them much earlier. And so if you haven't seen these before, you're in for a treat. I think, as I hope to illustrate, these really are truly spectacular objects. Okay, then in the third part, I'll state the main results and roughly outline the method that we use, giving the main steps of the procedure. And then we'll specialize even further to a particular example, and I'll show how the method works in a little bit more detail for that particular example, this 8-dimensional hypersurface, minimal hypersurface in the 9-sphere. So the ambient space for us, M, will be the round sphere of constant curvature 1. And let sigma, again, denote a minimal hypersurface, always assuming compact, connected, and oriented, smooth. And so a question you might ask is, which minimal hypersurfaces in the round sphere are stable? Right? Which ones are stable? And the theorem of Simon says none of them are. So that raises the following question. Given a minimal hypersurface in the round sphere, how far is it from being stable? Right? Can we measure that somehow? And we can. So remember that the stability means that the second derivative of area is non-negative. So we need a formula for the second derivative of area. Okay, so that's given by the so-called second variation formula. It goes like this. Let nu again be our unit normal vector field. And given a function f on sigma, we can consider the variation iota sub t, whose variation vector field is f times nu. Then the second derivative of area at time t equals 0 is given by this integral. It's given by the integral of f j sigma f, where j sigma f is what's called the Jacobi operator. This is a second order, a strongly elliptic operator. Okay, so you'll notice that there's the Laplacian, right? That's the second order term. And then you have those two 0th order terms, right? So the norm squared of the second fundamental form and then n minus 1. Okay, so the point here is that this operator, the Jacobi operator, it encodes, the second derivative of area essentially. And so in order to answer this question of, how far is a minimal hypersurface from being stable, it suffices to look at the Jacobi operator. So again, the Jacobi operator, this is a strongly elliptic operator. So by the spectral theorem, it may be diagonalized. So it's a classical fact that standard fact that the Jacobi operator has real eigenvalues, and these form an increasing sequence. I'm going to denote the eigenvalues mu1, mu2, up to mu s. Okay, so mu s will be 0, and then the positive ones are mu s plus 1, etc. And moreover, their multiplicities are finite. So we'll let L1, L2 up to Ls minus 1 denote the multiplicities of the negative eigenvalues, Ls the multiplicity of the 0 eigenvalue, and so on. Oh, and I should say that my convention is that the Laplacian is negative definite. So using these numbers, these numbers are, geometric invariants of your minimal hypersurface. And from these numbers, the eigenvalues and their multiplicities, you can construct, some very well-known and well-studied invariants, such as, for example, the Morse index and the nullity. Okay, so the Morse index, roughly, the Morse index is essentially the number of variations that decrease the area to second order, roughly speaking. And that's just equal to the sum of the multiplicities corresponding to the negative Jacobi eigenvalues. And similarly, the nullity is, again, roughly speaking, the number of variations or deformations that preserve area to second order. Okay, and that's just the multiplicity of the 0 eigenvalue. Right, so the index then measures the failure of our minimal hypersurface from being stable. And so given a minimal hypersurface, what you'd like to do in the round sphere, what you'd like to do is just compute the Morse index and compute the nullity. Okay, unfortunately, this is extremely difficult. if you pick a minimal hypersurface at random, computing the index, the nullity is essentially not feasible. You'll notice that the Jacobi operator contains the Laplacian, right? So it's strictly more complicated than, in a sense, computing the spectrum of the Laplacian, and we know how difficult that is, right? Even in the case where sigma is a homogeneous space, computing the spectrum of the Laplacian is quite difficult. So for that reason, geometric analysts tend to, the best we can do generally is to, prove estimates. And this is, a big industry. Geometric analysts like to, establish estimates that relate the index and the nullity to, for example, the curvature, the topology, the area, these sorts of things. But today we're going to be interested in attempting at least to compute the index and the nullity explicitly, for some highly symmetric minimal hypersurfaces. So let's give some examples. This has all been very abstract. So the most basic example of a minimal hypersurface in the round sphere is just the equator. So you take the round sphere and you cut it with an equatorial hyperplane. And it is known, shown by Jim Simons, I believe, that the index of the equator is 1 and the nullity of the equator is n. In fact, he proved more. He showed that if you have a minimal hypersurface in the sphere, then in fact, the index is at least 1 and the nullity is at least n. An equality in either one of these inequalities characterizes the equator. Okay, so these give us lower bounds for the index and the nullity. Okay, good. So we can compute the index of something. Let's see how far we can push this. Let's try to compute the index of something else. Okay, so the second simplest minimal hypersurface in the sphere, I would argue, are the Clifford hypersurfaces. Okay, so this is a product of spheres of the given dimensions p and q, where p plus q equals n minus 1. Okay, so I don't know who showed this first, but it essentially follows from the computation regarding the equators, together with knowledge of how the Laplacian of a product works, that the index of the Clifford hypersurfaces, it's n plus 2. And the nullity, moreover, is p plus 1 times n minus p. And it's been shown, I believe, by Oscar Perdomo that if sigma is a minimal hypersurface and not the equator, then in fact the index is at least n plus 2. And it's currently still an open problem to characterize those minimal hypersurfaces with index equal to n plus 2. Okay, Perdomo has shown that this is true under a symmetry assumption, and Francisco Urbano has shown that this is true. I say this is true. It has characterized the Clifford hypersurface as the unique such with index n plus 2. Urbano has shown this in the case n equals 3. In fact, that was a very important ingredient in Marquez and Nev's resolution of the Wilmore conjecture. So having these sorts of characterizations is quite powerful. Okay, but the general problem remains open. Okay, so we've successfully we have knowledge of the index and the nullity explicitly for the two simplest minimal hypersurfaces in round spheres. Let's keep going. How far can we push this? What then are the next simplest minimal hypersurfaces in spheres? And I would argue that they are the isoparametric minimal hypersurfaces. So what are those? So we need two definitions. Again, let sigma be a hypersurface, but now not necessarily minimal for now. We'll say sigma is homogeneous if it's the orbit of an action of a Lie subgroup of SON plus 1. Okay, so SON plus 1 is acting on Rn plus 1 in the usual way. Okay, and a homogeneous hypersurface is the orbit of an action of a Lie subgroup. And we'll say sigma is isoparametric if its principal curvatures are constant, right? If all of the principal curvatures are constant. Here I'm using G to denote the number of distinct principal curvatures, right? So G is some integer between 1 and n minus 1. Okay, remember that the principal curvatures don't have to be distinct. Okay, so notice that every homogeneous hypersurface is automatically isoparametric, and every isoparametric hypersurface is either minimal, meaning the mean curvature is 0, or CMC. CMC meaning constant mean curvature, where the constant is not 0. So the study of isoparametric hypersurfaces is quite old. It goes back to Elie Cartan in the 1930s, who studied these quite intensively. Well, yeah, he has some very foundational results on isoparametric hypersurfaces that I'll mention later. And then the subject, didn't receive that much attention, relatively speaking, for the next, 30 years or so. And then interest in the subject was revived by, papers of Munzner. And Munzner proved some really, truly amazing results. And I'm going to summarize some of Munzner's results in these two results that I'm going to name theorems A and B. Okay, theorems A and B are not their actual names. I have to call them something. Okay, so Munzner showed the following. Suppose sigma n minus 1 is an isoparametric hypersurface in the sphere. He asked the question, what can G be? How many distinct principal curvatures can there be? Seems like any number could show up between 1 and n minus 1, but Munzner showed that's not true. G, the number of distinct principal curvatures, can either be 1, 2, 3, 4, or 6. 1, 2, 3, 4, or 6. These are the only options for the number of principal curvatures in any dimension. Okay. So this is the first in a series of striking miracles. The second is that the cone on sigma, right? So you take sigma and you shoot rays through sigma, from the origin. And the cone on sigma, it turns out, is a real algebraic variety, right? Keep in mind, we didn't assume, homogeneity or anything. All we assumed was that the principal curvatures are constant. And then it turns out that the cone on sigma is a real algebraic variety, so it's the zero locus of some homogeneous polynomial. And what is the degree of that homogeneous polynomial? It's G, the number of distinct principal curvatures. So this polynomial has degree 1, 2, 3, 4, or 6. Okay, so the miracles continue. So capital F, that polynomial that cuts out our isoparametric hypersurface, that's nowadays called the Cartan-Munzner polynomial. Okay, so let's study it a bit more closely. Let's let little f denote its restriction to the n sphere. Then it turns out that the range of little f is the closed interval -1 to 1, and -1 and 1 are the only critical values of little f. So, once you know that, you're inclined to study the level sets of little f. So there's two cases. There's the case where you look at level sets at height C, where C is strictly, in the open interval -1, 1. And then there's the case where C is -1 or C is 1. So if C is in the open interval -1, 1, then it turns out that every one of these level sets, all of these preimages are isoparametric hypersurfaces, right? So you started off with one of them, and now you actually get sort of this family of isoparametric hypersurfaces, and all of them have G distinct principal curvatures. And moreover, if you order the principal curvatures like so, kappa 1 greater than kappa 2, etc., then amazingly, their multiplicities alternate. Okay, so their multiplicities are like m plus m minus, m plus m minus, so 1, 2, 1, 2, where it could be the case that m plus equals m minus. But the point is that the number of distinct multiplicities is at most 2. Moreover, in this family of isoparametric hypersurfaces, right, all of which are CMC, it turns out that the only minimal one is the one with C equals 0. Okay, so this is a very nice, fact about the level sets when C is between -1 and 1. And so you might ask what happens at C equals 1 or C equals -1. I'm going to denote those level sets by V plus and V minus. Okay, it turns out that those two are minimal submanifolds. Those are called focal varieties. And they are minimal submanifolds of high codimension. And what are the codimension of those minimal submanifolds, you ask? In fact, the codimension of V plus is M plus plus 1. So the multiplicity of the first principal curvature plus 1. And similarly for V minus. So this is an extremely beautiful picture. Oh, and one last fact I forgot. There's a geometric interpretation of this function little f, right? The restriction of the polynomial to the n sphere. It turns out that it's equal to cosine of g times the distance to v plus. Okay, so in particular, the distance between V plus and V minus is pi over G. And again, G can only be 1, 2, 3, 4, or 6. Yeah, so kind of geometrically, I suppose, what you have, according to F, F, if you consider the level sets of F, right, you get what is essentially a sort of a foliation of the round sphere by isoparametric, hence CMC hypersurfaces, with the exception that these caps, these caps here are high codimension minimal submanifolds, right? So here you have sigma 0. This is, a minimal hypersurface. And then you have, I don't know, sigma 1/2, sigma 3/4, sigma 5/6 or whatever. And these are all CMC. And then here the sort of north polar ice cap or something is, that's a minimal submanifold of high codimension. So it's just a very beautiful way of breaking up a sphere, into pieces. And in fact, all of these, I find that these particular hypersurfaces and high codimension submanifolds, they seem to show up quite a lot in various contexts. Okay, so a problem that's received a lot of attention, over the decades is this. Can you classify the minimal isoparametric hypersurfaces in spheres? This has been a question that's received a lot of attention from a lot of people over the years. Right, so among the minimal isoparametric hypersurfaces are the minimal homogeneous ones. These were classified by Xiang and Lawson. I'll show the list on the next slide. And it turns out that there are 5 infinite families and 9 sporadic exceptions. And okay, so that covers the homogeneous case, but what about, are there inhomogeneous minimal isoparametric hypersurfaces, for example? Well, it turns out for G equals 1, 2, and 3, the answer is no. Cartan in the 30s showed that if G is 1, 2, or 3, then being isoparametric, meaning that the principal curvatures are constant, that forces your minimal hypersurface to be homogeneous. However, the situation is amazingly completely different for G equals 4. For G equals 4, inhomogeneous examples were constructed by Ozeki and Takeuchi in 75, and then Ferris, Kartner, and Munzner in 81. And then finally, a classification of the, very involved. I don't actually know it, the classification of the G equals 4 case. I'm not an expert on this, unfortunately, but I'm aware that there is a classification of minimal isoparametric hypersurfaces with G equals 4 distinct principal curvatures. And this was finally completed relatively recently by Chi in 2020. So this is the result of a series of papers by many people, Stolz, Cecil, Chi, and Jensen, and then Chi in 2020 is when the classification was completed for G equals 4. For G equals 6, as far as I'm aware, only 2 examples are known. Both are homogeneous. And of course, the homogeneous ones are classified, but the inhomogeneous ones, it's not clear whether any inhomogeneous ones exist as far as I'm aware. And classification is an open problem. A classification was claimed a few years ago, and I think that classification for the G equals 6 case was accepted for a certain number of years, and then unfortunately it was turned out that that was in error. So the G equals 6 case is still open. There are partial results due to Dorfmeister and Nair. And my understanding is that, in the G equals 6 case, the only options are for the minimal isoparametric hypersurface to live in either the 7 sphere or the 13 sphere. And I believe that the only remaining case is the 13 sphere. So that's somehow the only thing that's left in terms of the classification. So here now is the list of the homogeneous minimal, sorry, I should say the minimal homogeneous hypersurfaces and spheres. So for G equals 1, we've already met these. These are the equators. Okay, those are all of them. And for G equals 2, those are the Clifford hypersurfaces, which we've also seen. Now for G equals 3, again, this is due to Cartan, it turns out that there's only 4 of them, literally just 4 homogeneous minimal hypersurfaces with 3 distinct principal curvatures, and here they are. Okay, there are those 4. Okay, they're of dimension 3, 6, 12, and 24. And you may notice that their dimensions are 3 times 1, 2, 4, and 8, which are the dimensions of the real numbers, complex numbers, quaternions and the octonions, and that's not a coincidence. These four minimal hypersurfaces are indeed related to the reals, complexes, quaternions, and octonions. For example, the focal varieties in these cases, remember those are the high codimension minimal submanifolds at the sort of polar ice caps. Those focal varieties are, in these cases, RP2, CP2, HP2, and OP2. So for G equals 3, the situation, as you can see, is quite sparse. There's only 4 of them. So you might think that for G equals 4, well, you might wonder whether there's a lot or whether there are very few, in the homogeneous case at least. And it turns out there's quite a few for the G equals 4 case. There's these 3 infinite families and 3 sporadic exceptions in dimensions 8, 18, and 30. Yeah, so the G equals 4 case, again, is somehow the richest and most complicated. And then finally in G equals 6, again, it returns to being very rigid. For G equals 6, those are the only 2 isoparametric ones that we know with 6 principal curvatures, one in dimension 6 in the 7 sphere, and the other is a 12-dimensional hypersurface in the 13 sphere. And both of them seem to be related in some way to G2. So I would argue that these are the simplest minimal hypersurfaces in spheres. And given that these are the simplest, we should at least attempt, I think, to try to compute their Morse index and nullity. So we did that for G equals 1 and 2, and now we should see whether we can do this for more of these. So let's let sigma be any one of these homogeneous minimal hypersurfaces. And again, G is the number of distinct principal curvatures. So in the in this case, the Jacobi operator simplifies somewhat. The second fundamental form term is now essentially just a constant times the identity. So our Jacobi operator is now just a shift of the Laplacian. So the point is that in order to compute the Morse index and nullity, all we have to do is compute the spectrum of the Laplacian. How hard could that be? So let's recall that J sigma, my notation for the eigenvalues are mu1, mu2, and so on, up to mu s minus 1. Those are the negative Jacobi eigenvalues. Mu s is the one with the 0 eigenvalue, right? And I'm asking, can we compute the index, which is the sum of the eigenvalues for the negative, the sum of the multiplicities corresponding to the negative Jacobi eigenvalues, and can we compute the nullity, right? And again, clearly we need the spectrum of the Laplacian in order to do this. So for G equals 1, 2, and 3, this has been done. Right, for G equals 1 and 2, we talked about this earlier. And for G equals 3, this was done in 2 papers by Bruce Solomon. Okay, so in the first paper, he looked at the hypersurfaces of dimensions 3 and 6. And then in the second paper, he considered those of dimensions 12 and 24. These are really sort of 2 very beautiful papers of Bruce Solomon, and these are the Morse indices and nullities that he computed. I'll let you all look at this for a second. Okay. So for G equals 1, 2, and 3, we know the Morse index and the nullity. What about 4 and 6? Well, that's been an open problem for some number of years now. For quite some time, we didn't know any of for all of these on this list. It was an open problem to compute the index and the nullity. So all of this, all of the blank space on this table here, that got Gavin Ball and Uwe Semmelmann and I to talking, and we felt that this sporadic 8-dimensional example, SO5 mod T2 in the 9 sphere, was quite beautiful, and we started looking at that quite intensively. And so the first result I'd like to advertise is that SO5 mod T2, that 8-dimensional minimal hypersurface in the 9 sphere, has Morse index 275 and nullity 35. And so we were very happy to compute the index and nullity there. And so we started looking at least one of the others. It would be nice, for example, to compute the index and nullity of some of these infinite families. And so far, we don't know whether we can really do that. The infinite families are somewhat daunting. We're hoping that maybe some sort of induction argument could work. We don't know to what extent an induction argument would be feasible. It's something we're talking about. But if an induction argument were to work, then at minimum, you'll need the base case. And so for the first of these families, it turns out that the base case is k equals 3, and the Morse index is 39, and the nullity is 11. Okay, so this now is the state of the art. Every entry in this table, which is not filled in, remains an open problem. Okay, so I want to talk in more detail about these results before explaining the method. But I should say that our method is essentially, it's essentially Solomon's method. Okay, this is we took the method that Solomon used in his paper about the G equals 3 case, and we refined his method somewhat. We sort of made it slightly more algorithmic, and we made it a bit more general in a certain sense. So it's worth maybe understanding what happens in the G equals 1, 2, and 3 cases, because the situation is somehow quite different in the G equals 4 case, even though the method is essentially the same. So in the G equals 1, 2, and 3 case, Jim Simons and Bruce Solomon were able to derive an explicit formula for the eigenvalues. Okay, and by an explicit formula, I mean they get some sort of polynomial, and you just plug integers into this polynomial, and out come the eigenvalues, right? You sort of have a parametrization of the eigenvalues. They're given by, some sort of polynomial with, complicated polynomial with integer coefficients, but in particular, they get an explicit formula, and the spectrum of the Laplacian consists of integers. However, when we looked at these two minimal hypersurfaces, okay, this 4-dimensional one in the 5 sphere and this 8-dimensional one in the 9 sphere, Gavin, Uwe, and I were unable to get an explicit formula for the eigenvalues. Unfortunately, the best we could do was get an algorithm so that generates the eigenvalues. So what do I mean by an algorithm? I mean this: you give me a negative number, let's say negative 100, and our algorithm spits out the eigenvalues of the Laplacian from 0 to negative 100. Okay, so it's not so much a formula so much as it is a process. More specifically, you give me this number, negative 100, and the algorithm produces a finite list of finite dimensional matrices. And when you compute the eigenvalues of that finite list of finite dimensional matrices, you get the eigenvalues of the Laplacian from 0 to negative 100, as well as some others that are even lower. But for sure, you at least got the ones in the range that you wanted. So you might say, well, maybe that's disappointing, right? Well, why couldn't we get a formula? Why did we have to settle for an algorithm? But we think that there's a good reason. It turns out that for these two minimal hypersurfaces, the spectrum doesn't just contain integers. It also contains irrational Laplace eigenvalues, some of which are not expressible in radicals. So that's a really striking difference in the G equals 1, 2, and 3 case. And that, having irrational numbers not expressible in radicals, that, sort of hard to imagine what a formula for such a thing would look like. So just to give an illustration of, how wild, sort of this, there's kind of this bizarre mix of order and chaos in the eigenvalues. And I just want to show you what the negative ones, the non-positive ones look like. So for the 4-dimensional hypersurface, some of the, among the non-positive Jacobi eigenvalues, okay, among these there's this arithmetic sequence, negative 16, negative 12, negative 8, negative 4, and 0. And in fact, this was discovered by Bruce Solomon in a separate paper in the 90s. So these eigenvalues here were already known prior to our work. It just wasn't clear whether there were any others. And for sigma 8, again, there's this arithmetic progression. Okay, negative 32, negative 24, etc. And then these eigenvalues were known, again, due to Bruce Solomon, who studied the quartic case. But it wasn't clear whether there are any others. But we now have an exhaustive list, and I'm sure you can all see the pattern. They're exactly what you think they are. Yes, here are the other. This is a complete list of the non-positive Jacobi eigenvalues. They're just exactly what you would have thought, of course. 4 radical 5 minus 24, and so on. Here, I should say that these 14.2 and 4.6, those are expressible in radicals. It's just that the radical expression is so gigantic that I didn't want to include it. The eigenvalues that are not expressible in radicals are all they're positive. Okay, so they're not here. Okay, so we didn't just compute the eigenvalues, we also have their multiplicities. You add up those multiplicities, and that's how we got the index and nullity. So let me talk a little bit in the remaining time about the technique. So our method was a refinement and an extension of Solomon's technique. And broadly speaking, it's a sort of a four-step process. I should say that all four of these steps, unfortunately, are quite non-trivial. So, in a sense, this is an algorithm, but on the other hand, you do have to work quite hard for each of these steps. So here's what you do in broad terms. Let sigma be G mod H, right? So that's our homogeneous minimal hypersurface. So the first step is to decompose the space of L2 functions into G invariant pieces. So these are the isotypical summands. Okay, so you do this using a result called Frobenius reciprocity. And Frobenius reciprocity, tells you, what these isotypical summands are. It says, well, it tells you what these are and what the multiplicities are, but computing the multiplicities can be quite hard. And so that's the non-trivial part. It's not so much Frobenius reciprocity itself, it's more computing the multiplicities of these W1, W2s, and so on. I'll say what I mean by that in a minute. And then the idea of the method is to essentially compute the Laplacian on each isotypical summand. So you want to represent the Laplacian on W1 as a matrix, and you want to represent the Laplacian of W2 on a matrix. And the Laplacian preserves these WJs because of the G invariance of the Laplacian. So you want to essentially, well, if you like, diagonalize the Laplacian. That's somehow the idea. So in order to represent the Laplacian as a matrix, you have to choose a good basis. So you have to choose a basis of W1, choose a good basis of W2. And the way you do this is you choose what I'm going to call a generating basis, B sub j of Wj. I'll say what this is in a few more slides. But essentially, this is a finite set of functions. And it doesn't exactly span Wj. It spans a much smaller subspace of Wj. But the point is that by G invariance, it's somehow this very small, relatively small collection of functions is somehow enough to understand the Laplacian on all of Wj. The fact that Bj doesn't span all of Wj, I should say, is a feature, right? The fact that Bj is so small is a good thing. Okay, so therefore, what you can do is, for each of these functions, each of these basis functions, f, you now have to compute the Laplacian of f and express the result in terms of the basis functions. And I should say that this is actually quite non-trivial. I was quite stunned at how hard this was. When we first started this project, I sort of thought, well, of course I can compute a Laplacian. I can take second derivatives, no problem, or at least I can get Maple to do it. The problem is, of course, you can compute the Laplacian, but can you express the result in terms of basis functions? That's actually quite tricky. Because these minimal hypersurfaces, in a certain sense, are not really parametrized, right? They're level sets. And so you kind of need, you need to get the computer to understand that you're working on a level set, right? You need it to understand that the Cartan-Munsner polynomial is 0. And getting it to do that is not so easy, actually, forcing the cancellations. So you actually have to work quite hard to somehow compute these Laplacians in a useful way. But once you do that, yes, now you have the matrix of the Laplacian on each isotypical summand. And so this is enough to, get an algorithm for the spectrum. Right, so steps 1 through 3 give you an algorithm for the that generate the eigenvalues and their multiplicities. But, if you're interested in the Morse index, you don't want this procedure to go on forever. You need this process to terminate after finitely many steps. So you need to know specifically which WJs, right, which isotypical summands house eigenvalues relative, that are relevant to the Morse index. So you need to know which WJs house eigenvalues in the kind of relevant range. So to that end, we derive an upper bound. Yeah, we for a given WJ, we show that all of the eigenvalues of the Laplacian on Wj are at most some number. And the point is that if this number is less than or equal to negative g times n minus 1, well, then that wj has no eigenvalues relevant to the Morse index. And so that actually rules out all of the wj's except for finitely many. And so that finally, at the end of the day, reduces the calculation of the Morse index to a finite calculation, right? You end up getting a finite list of finite dimensional matrices. Okay, so this was essentially Solomon's method. Solomon had steps 1 through 3, but he didn't need step 4 because, again, he had this explicit formula. So our sort of extension is step 4, and we've sort of taken 1 through 3 and made it slightly more algorithmic. So you may notice that nothing in this procedure really assumed that sigma is a minimal hypersurface, right? This seems to work as far as we can tell for any homogeneous space, right? This works sort of in sort of complete generality for any Riemannian homogeneous space, right? It doesn't have to be, normal. Yeah, I should mention that. I should have said this earlier. These homogeneous spaces that we're working with, these are not normal homogeneous spaces, right? The metric is sort of, it's just some homogeneous metric, as I'll show you soon. The metric is not Einstein or anything. So this is really a quite general process. So, we would like to, we're hoping that in the future we can really showcase the power of this method and use it to compute a bunch of things. For example, it would be nice to compute the Morse index and nullity of, for example, this infinite family. We've done this for k equals 3, and it would be nice to do this for higher values of k. We're still talking about this. But again, in view of the generality of this method, we're hoping to show that this method doesn't just give you the Morse index of minimal hypersurfaces, but maybe also of some high codimension minimal submanifolds as well. So this is something we're talking about, applying this method to high codimension minimal submanifolds, which are, of course, much more challenging. And potentially, certain aspects of this method might help compute the index of certain free boundary minimal hypersurfaces with a lot of symmetry in the unit ball. We'll see. I mean, this is something we're still working on and discussing. But in my remaining time, let me just illustrate a little bit more concretely at least steps 1 and 2 of the method, and let me talk about this very beautiful 8-dimensional minimal hypersurface in the 9 sphere. So I want to think of R10 not as R10 itself, but as little SO5. I want to think of R10 as little SO5, the set of 5 by 5 skew symmetric matrices. And so S9 is the set of those matrices with norm 1. And so inside that, the 9 sphere, we can form the set sigma. Okay, the set of 5 by 5 skew symmetric matrices with these eigenvalues. And it turns out that this sigma is, in fact, this is a homogeneous minimal hypersurface. This is SO5 mod T2. This is, if you like, SO5 is acting, the Lie group SO5 is acting, on the Lie algebra SO5 by the adjoint action. And this is one of the adjoint orbits. Right? This is the minimal adjoint orbit in the 9 sphere. So it has it's also equivalently, it's cut out by a quartic polynomial, namely the Cartan-Munzner polynomial. And here it is. This is the Cartan-Munzner polynomial. Here we're thinking of R10 now instead of as skew symmetric matrices as 2 forms on R5. This is a quartic polynomial, and this 8-dimensional hypersurface is this level set. The isotropy representation decomposes into 4 T2 irreducible pieces. Okay, you can write the metric like so, where H is the negative of the killing form of little SO5. And as you can see, there's no repetitions here in these numbers in the metric. They're all different. The metric on sigma is not Einstein. I mean, yes, it's homogeneous, but this is not the normal metric. Not an Einstein metric. It's just this one. As far as we can tell, the interesting geometric features of this metric are, well, that it's the induced metric of a homogeneous minimal hypersurface. That's what recommends it. So the first step, so we want to run this 4-step process, and I don't have time, unfortunately, to showcase all 4 steps, but let me at least give some indication as to what steps 1 and 2 look like in this example. So you need some representation theory, of course. So let's let VKL denote the irreducible complex SO5 representation of highest weight KL. The dimension of these can be calculated by Weil's dimension formula. We only need VK even, VK odd won't be relevant. And so here are some of your favorite, some of my favorite representations, at least, some simple ones. And so step one, like I said, is to decompose the space of L2 functions into isotypical summands. And so Frobenius reciprocity does that abstractly, but it doesn't tell you what these and it gives you a formula for these multiplicities, but that multiplicity formula is not really as explicit as you would like. So you need to, call up your representation theory friend, call up your local representation theorist and figure out how exactly to calculate this MKL explicitly. And in this case, SO5 mod T2, we were lucky that this was sort of somehow not that complicated. And here, these end up being the multiplicities, and the ones with odd, VK odd ends up not being relevant. So, okay, so we have this decomposition. If you like, this is sort of a Fourier decomposition of the L2 functions. And what we want to do is compute the Laplacian on each of these isotypical summands. But in order to do that, we need a good basis in which to compute the matrix. And this is step two. And yeah, so this is Solomon's technique. So a definition, first of all, so given an SO5 equivariant function on sigma, right, that's valued in VKL, its associated highest weight function is this. You take Z and then you compose it with the projection onto the highest weight subspace, which necessarily has complex dimension 1. So here what we're doing is we're choosing, we haven't written this, but we've chosen a highest weight vector in each of the highest weight subspaces. And it turns out that the set of highest weight functions is a vector space. And it has and not just a vector space, it has all of these really nice properties. And the properties of these highest weight functions are really crucial, right? This is really the engine that makes this procedure work. And so, right, the highest weight functions is a complex vector space of this complex dimension. It's exactly the multiplicity that appears here. And moreover, it turns out that you can, represent this isotypical summand sort of more concretely, like so. It's up to G and up to the G action. So in this case, up to the SO5 action, it's essentially given by these highest weight functions, right? So this is how you can get your hands, in principle at least, on kind of basis functions for these isotypical summands. So what you need to do then is you need to find a basis, BKL. You need to find a basis of the highest weight functions. And those are the functions that you work with. Those are the functions whose Laplacians you end up computing. Okay. Of course, to find this basis of highest weight functions, well, we need a large supply of highest weight functions. So that means we need a large supply of equivariant functions. So in the SO5 mod T2 case, we were able to find these 5 SO5 equivariant functions. And the sort of key point is that these 5 SO5 equivariant functions on sigma, on the 8 manifold, are in a sense enough to generate a basis for for all of the highest weight functions, right? So all of the highest weight functions on sigma can be obtained as monomials in these highest weight functions, where these are the highest weight functions associated to these equivariant functions. And the point is that we were lucky that somehow there are only 5 of these. We attempted some of the other minimal hypersurfaces on that list. And for some of the other more complicated ones, you get far more than 5. You get, 10, 12, 14 of these things. And that makes this procedure, this is very computationally intense. Okay, so the upshot finally is that you can, you then calculate the Laplacian of f for each of these basis functions, and you express the result in terms of these basis functions, which gives you this matrix. And at the end of the day, that enables you to extract the eigenvalues of the Laplacian, as well as their multiplicities. The multiplicities are the dimensions of these spaces. And so there you go. If you add up these numbers, you do in fact get the Morse index 275. And here, of course, the nullity 35. And so the last thing I'll say is I frequently get asked about, geometric interpretations of the index. There are, for the G equals 1 and 2 case, well-known geometric interpretations. And here, I suppose, the geometric interpretation of the number 275 is that it's the sum of these numbers, each of which, if you stare at it, sort of has a geometric interpretation in terms of sort of representation theory, as well as these functions here, the position function, the normal vector, and then these sort of polynomial combinations of these. And that's, I think, kind of the best you can do for a geometric interpretation of the index. Okay, well, thank you for your time. Thanks for your attention and for having me back.
Thank you for a really beautiful talk. Are there any questions?
Can I ask a quick question then? Also, amazing exposition, by the way, very clear. Very much enjoyed listening to it. So you mentioned briefly some current interest in the high codimension case. I'm also very interested in the high codimension minimal surfaces. In particular, here, if you look at the focal ones, right? Is that done for the focal ones and for small g? Is that, I mean, besides the trivial cases?
I don't believe so. I think even for G equals 3, that's open. Yeah, we started talking about that a little bit, and then, well, we have too many things that we would like to do. We can't do everything all at once, unfortunately. Yeah, as far as I'm aware, I believe that the index for the RP2, CP2, HP2, OP2, I believe the index of those is still open. Maybe RP2 is known. Actually, I think RP2 is known.
Veronese embeddings, right?
Yeah, the Veronese embeddings. Yeah, but I think for CP2, HP2, and OP2, I don't think that's known.
I would find it.
Francisco Urbano might know, and Teraldo might know.
And one thing that kind of comes up when you're looking at this high codimension thing is that then the slice representation is no longer trivial, right? When you're in the hypersurface case, it's a principal orbit, and the slice representation is trivial, so equivariant sections kind of behave nicely. But in the high codimension case, these are isolated in orbits, right? So how does one, I mean, you have to look at the Laplacian acting on sections of this normal bundle, but it's no longer a trivial bundle, right? So that's
that's a difficult thing.
Machinery, but I guess, does the representation theoretic machinery go through still? I mean, when you said like try to adapt the same method, I mean, is that feasible?
We hope so. We're cautiously optimistic. So yeah, that's I think where our attention is at the moment, sort of to trying to work on some of these high codimension things.
Got it. Thank you.
We will see. I'll let you know if things explode.
Are there other questions? You mentioned looking at the case of perhaps free boundary minimal hypersurface. Would that involve the Steklov spectrum instead, or would that still be?
Yes. So those wouldn't even be homogeneous. Those would be cohomogeneity 1. Yeah. So here, here, this is a very liberal use of the word adapt the method. Yeah. I mean, for this last bullet point, I really mean something, sort of. Yeah. These would be cohomogeneity 1, and I think for some of these cohomogeneity 1 free boundary minimal hypersurfaces, I again am cautiously optimistic that you can compute enough of the Steklov eigenvalues to get this. Again, this is cautious optimism here. Yeah,
well, that's great. Are there any other questions? Well, thank you again. Really, really nice talk.
Thank you.